Okay, you're on to the additional practice for Chapter 10. Number 1. How many lone pairs are found in a caffeine molecule? Assume that there is 0 formal charge on all atoms. Not even assume, there really is. There's 0 formal charge on all atoms. So how many lone pairs do I have? In order to do this, you need to identify what it means to have a 0 formal charge. So in this molecule, we have carbon atoms, hydrogen atoms, nitrogen atoms, and oxygen atoms. The lone pairs are not listed. We often don't write lone pairs past writing Lewis structures. So we have to identify, does it fit the rules for formal charge of 0? Carbon wants 4 bonds. Hydrogen, 1 bond. Nitrogen, 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pair. So with that in mind, let's go through and determine what these fit. This carbon atom right here has 3 hydrogens bonded to it and 1 nitrogen. That fits the rule for 4 bonds. This carbon, 1 hydrogen, a single bond to a nitrogen, and a double bond to another nitrogen, 4 bonds. This carbon, a single bond to a nitrogen, a single bond to a carbon, and a double bond to a carbon, 4 bonds. This carbon, a double bond to a carbon, and 2 single bonds to 2 different nitrogens, formal charge of 0. This carbon, 3 hydrogens. Those are, the way this is written with CH3 is assumed that they are all singly bonded to carbon because hydrogen can't have more than a single bond. So 3 single bonds to hydrogens and 1 single bond to nitrogen, formal charge is 0. This carbon, a double bond to oxygen, 2 different single bonds to 2 different nitrogen atoms, formal charge is 0. This carbon atom, a double bond to an oxygen, a single bond to a carbon, and a single bond to a nitrogen, 0 formal charge. And this carbon, 3 hydrogens, those are all singly bonded, and a single bond to nitrogen, 0 formal charge. These hydrogens, and these hydrogens, the way they're written, mean they all have 1 single bond to that central carbon atom right there. This hydrogen has a single bond to the carbon atom here. Let's look at oxygen. This oxygen has 1 double bond, which means it's implied that it also has 2 lone pairs. This oxygen also has a double bond, which means it is implied that it also has 2 lone pairs. And this nitrogen has 3 bonds, which means it's implied that it has a lone pair. This nitrogen has 3 bonds, which means it's implied that it also has a lone pair. This nitrogen, 3 bonds, so implied that it has a lone pair. And this nitrogen, 3 bonds, so it is also implied that it has a lone pair. So let's add up those lone pairs. 1, 2, 3, 4, 5, 6, 7, and 8. The answer here would be D. What are the 2 most important factors in determining the magnitude of lattice energy of an ionic solid? Your 2 most important factors is size and charge. And remember, so what the trend is here, smaller size is increase in lattice energy. The smaller they are, the more they can feel the attraction. One ion can feel the other ion's nucleus attraction force. So the smaller they are, the tighter they fit together, the more energy it's going to take apart. The larger they are, the less they feel that pull, the easier they'll pull apart. In ionic charge, larger charge, more energy. So +1 is weaker than +2 is weaker than +3. Lastly, remember charge beats size. So if you can narrow it down and it comes down to either a charge or a size, the charge is going to lead to the higher energy. Determine delta H of the following reactions. So the first one, CH2CH2, this is ethene. We have a double bond in there and 2 carbons. Reacts with water to form ethanol. So let's draw these out. Okay, let's think about what we're breaking here. 1, 2, 3, 4 CH bonds, which are 414 kilojoules per mole. 1 carbon-carbon bond, double bond specifically, which is 611 kilojoules per mole. To break all of this, so 4 times 414 plus 611, this will take 2,267 kilojoules per mole of energy to break apart. Just for this. Water, I've got 2 OH bonds, which is 464 kilojoules per mole, which is 928 kilojoules per mole for both bonds. So 2 times this times 4. And for ethanol, I'm breaking 1, 2, 3, 4, 5, or not breaking, sorry. I'm forming 5 carbon-hydrogen bonds. So 5 times negative 414 kilojoules per mole. Remember, it's negative because the bond is forming, so it's releasing that energy. I've got 1 carbon-carbon bond here, which I forgot to write down. So let's see, 347. I've got 1 carbon-oxygen bond, which is 360 kilojoules per mole. And 1 oxygen-hydrogen bond, or OH bond, which is 464 kilojoules per mole. And these all have to be negative because the bonds are forming. And let me add that up quick because I forgot that 1 bond in there. 5 times negative 414, 1 times 347, 1 times 360, and 1 times 464. Oops. I'm really good at turning the eraser on. Negative 3,241 kilojoules per mole. Let me just check that since I'm trying to do this on my phone. Okay, so add these numbers up. I've got 2,267 kilojoules per mole to break up my ethene. I've got 928 kilojoules per mole to break up water. And I will release 3,241 kilojoules per mole when ethanol is formed. So 2267, 928, and negative 3241 gives me overall negative 46 kilojoules per mole. I'm going to write that in here. So overall, the delta H of reaction to react 1 mole of ethene with 1 mole of water to produce 1 mole of ethanol, delta H of reaction is negative 46 kilojoules per mole. Let's do that with the other examples as well. the combustion of 1 mole of ethane. Eth tells me 2, ane tells me single bond, which means carbon-carbon, 2 carbons with a single bond in between. So let's write that up here. CC, H, 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 H. So C2H6 reacts with oxygen. Oxygen does double bond to itself, because remember, oxygen wants 2 bonds, 2 lone pairs, and produces carbon dioxide and water. And I'll let you guys balance this out, but you should find this pattern. So in ethane, 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, but that's a 2 out here. So actually I'm going to multiply that by 12. 12 carbon-hydrogen bonds, 1 CC bond, but multiply by 2, so 2 CC bonds. 12 times 414 kilojoules per mole, and 2 times 347 kilojoules per mole. Overall, that gives me, hold on, I need to rewrite that, or re-add that, because that is not, I don't know where I wrote down this number. 414 times 12 plus 347 times 2 gives me 5,662 kilojoules per mole. And that's just for C2H6. I've got 7 waters. To break apart an OO double bond is 498 kilojoules per mole. Multiply that by 7. (3,486 kilojoules per mole). For CO2, I've got 2 CO double bonds, but note it's 799 in CO. That's for each bond. So that means 2 times 4, 8 times 799 is negative 6,392 kilojoules per mole. So this is for CO2. This is for water. And, or for, not water. Sorry, I'm thinking about your product. This is for O2. For water, I've got 2 OH bonds, which is 464 kilojoules per mole. But I've got 6 moles of it, which means 12 times that value. And I'm going to make it negative because it's a product and it's forming. So 12 times negative 464 is negative 5,568 kilojoules per mole. So add all that up. Positive 5,662 plus 3,486 minus 6,392 minus 5,568. Let me check that to make sure. Okay, so for this, for the complete combustion of ethane, we get negative 2,812 kilojoules per mole. Again, that is delta H of reaction. And the last one, the combustion of 1 mole of ethanol. Ethanol, Eth, 2 carbon, Ol, or OL is an OH, meaning an alcohol group. So CCOH plus O2 gives you CO2 and water. And if you balance this out, you're going to get 3 moles of water, 2 moles of CO2, 3 moles of O2, and 1 mole of ethanol. 1, 2, 3, 4, 5 CH bonds being broken. So 5 times 414 kilojoules per mole. 1 carbon-carbon bond being broken. 347 kilojoules per mole. 1 carbon-oxygen bond being broken. 360 kilojoules per mole. And 1 oxygen-hydrogen bond being broken. 464 kilojoules per mole. And add that up. This gives me 3,241 kilojoules per mole to break up your ethanol. O2, I've got an oxygen-oxygen double bond, but I have 3 of them. Oxygen-oxygen double bond is 498, but multiply that by 3, I get 1494 kilojoules per mole. Carbon dioxide, I've got 2 of them. Remember, though, that's that special case. I've got 2 bonds, and I've got 2 moles of it, which means 4 times 799. But it's going to be a negative number because I'm forming these bonds. Negative 3,196 kilojoules per mole. And water. 2 OH bonds, but times 3, so 6 OH bonds, because I have 3 moles of it. 6 times negative 464, negative 2,784. Overall, delta H of reaction here. So you've got positive 3,241 plus 1,494 for the reactants being broken up, minus 3,196 for CO2 being formed, minus 2,784 for water being formed. And overall, you get a delta H reaction of negative 1,245 kilojoules per mole. Okay. In the ion BrCl4-, how many lone pairs of electrons are around the central bromine atom? Br, 7 valence electrons. 4 chlorines, 4 times 7 valence electrons. 4 times 7, 28, plus 7, 35. Plus a negative charge, 1 valence electron, 36 valence electrons. Br, Cl, 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 Cl. Complete your octet on your outer atoms. I've used up 32 electrons, 34, and 36. The answer here? 2. There are 2 lone pairs on your central bromine atom. Consider the following 3 compounds, NaCl, MgO, and KBr. Based upon a consideration of lattice energy, which compound below is expected to have the highest melting point, which is expected to have the lowest melting point? Remember, melting point is related to how much energy does it take to break apart that lattice. So higher lattice energy, higher melting point. We've got NaCl, which is Na plus, Cl minus, MgO, which is Mg2 plus, and O2 minus, and KBr, which is K plus, and Br minus. Right away, I notice that this has the positive 2, -2 charge. This will have the highest melting point. Because it has the largest charge. Now we're comparing NaCl and KBr. What's going to have the lowest melting point? The compound that has the lowest melting point will have the lower lattice energy. If I look at the periodic table, sodium is above potassium, chloride's above bromine. These are these are larger. Larger ions, which means smaller lattice energy. Which means lower melting point. So this will have the lowest melting point. Write the Lewis structure, including formal charge, and all resonance structures if needed for the following compounds or ions. C2H6. Remember, hydrogens can only have one bond. Carbons want 4. You could add up the electrons if you wanted to, but the easiest way to do it is just draw this out. If you add up the valence electrons, you're going to find the same answer here. How about HCHO? The way this is drawn actually tells me how it's connected. It tells me H is connected to C, is connected to H, and all that's left is an O. Hydrogens cannot have more than one bond, so I know that that oxygen must be bonded to that carbon. In order to give carbon and oxygen its octet, I have to give it a double bond. These all have 0 formal charge. These also have 0 formal charge. C2H4, ethene. In order to give carbon its 4 bonds, I have to put a double bond in between. 0 formal charge. And C2H2. In order to give carbon its, in order to get rid of valence electrons and give carbon its formal charge, or its full octet, I need a triple bond in here, and these all also have 0 formal charge. Draw the best Lewis structure for the cation NO2+. What is the nitrogen-oxygen bond order? Remember, bond order tells me how many bonds are between the 2 atoms. One bond equals bond order of 1. 2 bonds, bond order of 2. A triple bond, bond order of 3. So NO2, nitrogen, 5 valence electrons, 2 oxygens, 2 times 6 valence electrons, overall 17 valence electrons, but I have a +1 charge, which means I'm taking away one of my electrons, giving me 16 valence electrons. Nitrogen, connect your oxygens, give your outer atoms their octet, 2, 4, 6, 8, 10, 12, 14, 16. I've used up all electrons. Check to make sure your central atom has it at its octet. This does not. Form double bonds as necessary. Now, this is my best Lewis structure. Some people may ask, why did I not just draw a single bond and a triple bond? I could, but here I've got a negative formal charge and a +1 formal charge. If I do that on the other side, same thing happens. They all have formal charge. That's a formal charge. That's a formal charge. Lone pairs all over the place. These are resonance structures. These are absolutely resonance. But it's asked me for the best Lewis structure. Best Lewis structure minimizes formal charge. What's the bond order here? 2. Bond order of 2. Bond order of 2. Double bonds. Write the Lewis structure, including formal charge, in all resonance structures if needed for the following compounds or ions. I'm not going to keep writing out the valence electrons all the time just because it takes a lot of time, but I recommend you guys do it until you get comfortable not having to do it. So CH4. If I added it up, I would find carbon has 4 valence electrons, hydrogen has 1. There's 4 hydrogens. Overall, 8 valence electrons, all single bonds. NH3 also has 8 valence electrons, 3 single bonds to hydrogen, and a lone pair on the nitrogen. NO2 minus, nitrogen has 5 valence electrons, 2 oxygens, which each have 6 valence electrons, and a -1 charge, overall 18 valence electrons. This has a -1 charge on it. And this is a resonance structure because there's no reason why I couldn't give the double bond to the other oxygen. Don't forget your lone pairs. And the -1 is over here. Now these contribute equally. Someone may ask, why can I not write a double bond from both sides? If I look at the nitrogen here, nitrogen has 10 electrons around it. Can't do it. Nitrogen is second period, meaning it does not have the space to do this. So do not do that. You could do that if you're in like sulfur, phosphorus, that kind of thing, that can do it. But nitrogen cannot do it. It doesn't have places to put those 10 electrons. More Lewis structures, formal charge, and resonance. So HC2H3O2, this is really hard for me to say. This is the way I write it. This is acetic acid. The way I write it is the way it's connected. Carbon with single bonds to 3 hydrogens, connected to a carbon, double bonded to an oxygen, bonded to an oxygen, bonded to a hydrogen. Everything in here has a formal charge of 0. HCN, hydrogen, 1 valence electron, carbon 4, nitrogen 5, overall 10 valence electrons. Give your outer atom its octet, 2, 4, 6, 8, 10. Check formal charge. Well, not even before you check formal charge, check to make sure your central atom has its octet. It does not. So nitrogen is going to donate electrons to form a triple bond to carbon. And now every atom has 0 formal charge. P2H4. I know that hydrogen can only have 1 bond, so my guess is that the phosphorus are going to be bound to each other and the hydrogen on the outside. 2 phosphorus is 10 valence electrons plus 4 hydrogen is 14 valence electrons. If you use 2, 4, 6, 8, 10, 12, and 14. If I check formal charge here, phosphorus is just like nitrogen. It wants to have 3 bonds and 1 lone pair. So everything on this page has 0 formal charge. Number 12 is definitely a more complex problem. So consider the three species, SO2, SO3, and SO3 2-. Excuse me. Draw the Lewis structures, being careful to obey the octet rule for each of these species. Based upon these Lewis structures, which should have the longest SO bond? Which should have the shortest SO bond? So let's go ahead and just draw out their Lewis structures first. SO2, one sulfur has 6 valence electrons, 2 oxygens, 12 valence electrons, overall 18 valence electrons. Sulfur in the center. Connect your oxygens. Complete your octets on your outer atoms. Right now I have given 16 of my 18 electrons out. Go ahead and put the remaining electrons on your central atom. Now just check if your central atom has an octet. It does not, so you're going to use one of those pairs of electrons to form a double bond to your central atom. Check your formal charge. 0, the sulfur, 6 valence electrons, minus 2 lone pair electrons, minus 3 bonds, plus 1. And the other oxygen, 6 valence electrons, 6 electrons involved in lone pairs, and 1 bond, overall -1 charge. Minimize your formal charge. How can I minimize my formal charge? I can do that by forming an additional double bond between my sulfur and my oxygen. Now, if I check, my sulfur will have 6 electrons, minus 2 lone pair electrons, minus 4 bonds, overall 0, and oxygen, when it has 2 bonds and 2 lone pairs, is also 0. So I've minimized formal charge. I've got all my electrons in. What about SO3? Sulfur, 6 valence electrons, 3 oxygens, 18 valence electrons, overall 24 valence electrons. I've used up 6 electrons so far, just connecting them. Now give everything give your outer atoms their octet. So 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. My outer atoms all have their octet now. Now check your central atom and make sure it has its octet. It does not. So I'm going to form an octet by donating one of those pairs of electrons, lone pairs, from one of your outer atoms to form a double bond with your central atom. Now it's left center. Now you could look at this and say, why did I give that oxygen the double bond? Doesn't matter which oxygen you gave the double bond to. It's going to go to one of them. This is one of the Lewis structures that's valid for this compound. If I... Ma'am. Sorry, it's only when I'm recording a video that my cat decides to try to play with whatever's right next to me. If I look at this overall charge, the oxygen here has a -1, oxygen here has a -1, the sulfur has a +2. Could I, in theory, donate 2 more pairs of electrons from the sulfur? Or from the 2 oxygens to form double bonds to sulfur? Yes, that would be a valid Lewis structure. Now, ring strain wise, it's going to push it if it can really do it, but we can draw it that way to minimize our formal charge. This is one of the resonance structures. We could also have, again, like we just had, sulfur singly bonded to the oxygen. I'm going to shrink these down. And SO3 2-. SO3 2- will have 6 electrons from sulfur, 18 electrons from oxygen, and 2 extra electrons from that -2 charge. So 26 valence electrons. It's connected very similarly to SO3. But we have a lone pair of electrons that goes to the central atom. Now, sulfur does have its octet, but if I want to minimize formal charge, I am going to go ahead and donate 1 pair of electrons to form a double bond to that sulfur. If I now check that sulfur now has a 0 formal charge, the 2 oxygens that each have 1 bond and 3 lone pairs each have a -1 charge. But the other oxygen and the sulfur both have 0 charge. I've minimized the formal charge. So again, these are resonance structures. Any oxygen could have gotten that double bond, but they would be equivalent. They would all be contribute equivalently or equally to the overall resonance structure. Which one's gonna have the shortest bond here though? Here, I've got 1 double, 2 single. Here I've got 3 double, 0 single. Here I have 2 double. What do you think is going to be the shortest bond? We won't talk about why they exist in this space until next chapter, but remember the triple bonds are stronger and shorter than double bonds. Double bonds are stronger and shorter than single bonds. So here I have 1 double, 2 single. Here I have 3 double, 0 single. I automatically expect this to be longer, this to be shorter. Now let's compare it to the 2 double. The 2 double will be 2 double compared to 1 double will be longer than SO3 2-, but it will be shorter than SO3 because it only has 2 double bonds, not 3 double bonds. So overall, my longest will be SO3 2-, my shortest SO3, and the middle will be SO2. Of the atoms listed below, which is the most electronegative? Boron, carbon, nitrogen, silicon, and phosphorus. Remember the trends of the periodic table. Electronegativity increases across and up the table. If I go across and up, I will find nitrogen. Also, nitrogen is the 3rd most electronegative, tied in place for 3rd with chlorine. Write the Lewis structure, including formal charge, and all resonance structures if needed for the following compounds or ions. Nitric acid. Nitric acid is HNO3. Hydrogen, 1 valence electron. Nitrogen, 5 valence electrons. 3 oxygens, 3 times 6, 18 valence electrons. So what is that? 18, 19, 20, 23, 24 valence electrons. I didn't actually write this out because I already know how to connect the compound. Nitric acid, by the way, HNO3. This is an oxyacid. It means that the hydrogen is attached to an oxygen. How do I don't know this? Well, I know it's an acid, and I know it has oxygens, so therefore it's an oxyacid. So if you have an acid, you know nitric acid is an acid, it says acid in it, and you've got oxygens in there, it will do this. The hydrogen will attach to the oxygen, not the central atom. So connect all your molecules, or connect all your atoms. Add your lone pairs. So far I've used up 2, 4, 6, 8 electrons. 10, 12, 14, 16, 18, 20, 22, and 24. Check to make sure your central atom has its octet. This does not have an octet, so you're going to use one of your lone pairs to create a double bond. It's going to be double bonded here. Why did I double bond it here and not another oxygen? Because this is a resonance structure. These are the two resonance structures. The oxygen that's bonded to hydrogen, it doesn't want to give a double bond to nitrogen because it already has its complete zero formal charge. It will be one of the other two oxygens that will form that resonance structure. So the electron density will be delocalized over this area. If I look at formal charge, +1, 0, 0, -1, 0, 0, 0, +1, 0, -1. Overall, it still has a zero formal charge, even though two of the atoms themselves have charges. I can't minimize further than that because nitrogen and oxygen can't have more than 8 electrons. And SF5-. So sulfur has 6 electrons, fluorine has 7 electrons, and I have 5 of them, and I have a -1 charge. Overall, this has 42 valence electrons. Sulfur in the center, connect to your 5 fluorines. Give everything its octet. So far I've used up 2, 4, 6, 8, 10 electrons, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Put your extra electrons on the central atom. Find your formal charge. When fluorine has 1 bond and 3 lone pairs, it is 0. Sulfur in the center, 6 valence electrons, -2 electrons in a lone pair, -5 bonds, overall has a -1 formal charge. Phosphorus trichloride, PF3. Phosphorus has 5 valence electrons, chlorine has 7, and there's 3 of them, so overall I have 26 valence electrons. Connect your fluorines. I think I said chlorine a minute ago. I meant fluorine. Same thing. They're both halogens. Give your outer electron or outer atoms their octet. I've used 24 electrons. I have 2 more to place, and I'll place those here. Overall, 26 electrons. If I looked at the formal charge, phosphorus is like nitrogen, where it wants 1 lone pair and 3 bonds. Everything here has a 0 formal charge. Your thiocyanate ion. Thiocyanate, thio means sulfur, cyanate, Cn. So thiocyanate, SCN-. Sulfur, 6 valence electrons. Carbon, 4 valence electrons. Nitrogen, 5 valence electrons, and a -1 charge. So 6 plus 4 is 10, plus 5, 15, plus 1, 16 valence electrons. It is connected the way the formula reads. Give your outer atoms their octet. Now, my central atom does not have its octet, so go ahead and form double bonds. There's a couple ways we can do this. I could have both sulfur and nitrogen each donate, or nitrogen and carbon can both actually have triple bonds. So the other thing I could do is have both electrons donated from that nitrogen, or both sets of electrons. Have a single bond to the sulfur, and a triple bond to the nitrogen. Now if I do formal charge here, if I look at sulfur right here has a 0 formal charge. Carbon has a 0 formal charge. Nitrogen, -1. In this case, nitrogen 0, carbon 0, sulfur -1. Who would rather hold the negative charge? The more electronegative element. Which one's more electronegative? Nitrogen is tied in 3rd place with chlorine. Sulfur is less electronegative than nitrogen, so this will contribute more. Which of the bonds below is expected to be the most polar? Well, they're all bonded to hydrogen. So what I'm looking for here is how electronegative this is compared to hydrogen. Since they're all comparing to hydrogen, then I can just say how electronegative are they to each other. This is pure covalent. So I've got carbon, nitrogen, chlorine, and oxygen. And not even intentionally, I wrote them in the order of increasing electronegativity. So number 2. These are tied for number 3. And I don't know where carbon falls in the exact sequence after that, but I know that oxygen is the second most electronegative. So therefore, this one will be the most polar of the bonds. Which of the compounds below exhibit predominantly covalent bonding? In order to answer this question, you really do need their values of electronegativity. So, hydrogen, 2.1. Chlorine, 3.0. Difference, 0.9, which is considered polar covalent. Magnesium, 1.2. Chlorine, 3.0. Difference, 1.8, which is on the extreme, but it is considered polar covalent. And above is considered ionic. It's not predominant though, it's on the extreme end. SCl2, sulfur, 2.5, chlorine, 3.0. Difference, 0.5. This one is on the other extreme of polar covalent, where it's barely outside of the nonpolar region. Nonpolar goes to a value of 0.4. And PCl5, phosphorus, 2.1, chlorine, 3.0, difference 0.9, polar covalent, and it's pretty much in the middle of that range. So this is closest to nonpolar, whereas this is closest to ionic. Write the Lewis structure, including formal charge and all resonance structures if needed for the following compounds or ions. I put these extra practice together. I didn't realize how many times I'd be doing this over and over again, but it is good practice for you guys. Okay, C2H6O. There are a few different ways I can actually put this one together. I could say this. This is an ether. Or I could say this is an alcohol. There's not enough information for me to tell which one is which, or which one it is. It could be either one. CH3CHO, the way that's written tells me that I have a CH3 group bonded to a carbon that's bonded to a hydrogen, and then I have an oxygen left. That will be double bonded to the oxygen. If you add up the valence electrons and look for minimizing your formal charge, giving your central atoms its octet, you will find that that oxygen does need to be double bonded to that carbon. And CH3CH2CH3 is written as it's connected. CH3, CH2, CH3. All of these have zero formal charge. Okay, the azide ion. Azide is one that, for whatever reason, is hard for me to remember. N3- is your azide ion. You've got 3 nitrogens, so 15 valence electrons there, plus a -1 charge, overall 16 valence electrons. We do have a resonance structure for this. So, because you've got 3 nitrogens bonded together, Overall 16 valence electrons. We can write this a couple different ways. We can do 2 double bonds. With 2 lone pairs on each external nitrogen. Here, -1, -1, +1. Or we could do a single bond between one nitrogen and the central nitrogen, and a triple bond between the central nitrogen and the other external nitrogen. If I do this, this nitrogen has a -2 charge, the central nitrogen has a +1 charge. And of course, we could also do the triple bond to the other side, but we see the same outcome. With a +1 charge here, and a -2 charge here, 0 here, and 0 here. It's going to prefer to minimize its formal charge. Now, we can't not have formal charge. It's going to exist, but this is going to be the preferred. So we can minimize formal charge. What about CH3, CH2, COO minus? This is propanate. Propanoate, or I say propanate, but propanoate is a conjugate base. You're going to learn about this next semester. I can't spell. You're going to learn that already. Of an acid. It's written out just like it's connected. So carbon connected to 3 hydrogens. Connected to a carbon, which is connected to 2 hydrogens, connected to a carbon, which is connected to 2 oxygens. If you add up all of the valence electrons, you're going to find the structure comes out like this, and this oxygen has a -1 charge to it. Why did I give that oxygen the single bond? Aren't these oxygens equivalent? Yep, this is a resonance structure. You could also draw this. Carbon, 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 double bonded to an oxygen, single bonded to this oxygen. And then this oxygen would have a -1 charge. The way this actually exists in the real world is that this charge here is delocalized over this area, meaning it's kind of a single and partial double bond character across this whole area. Number 20, cyanate. Cyanate, we just talked about thiocyanate, so hopefully you guys remember what that one is. Cyanate is just drop the thio, drop the sulfur, Cn minus. Carbon, 4 valence electrons. Nitrogen, 5 valence electrons. -1 charge, 1 extra valence electron, so we have 5 valence electrons. This is actually going to form a triple bond to try to minimize formal charge. Carbon has a -1 charge, nitrogen at 0. Carbon's not exactly happy about that. It doesn't want the -1 charge, but this is the actual structure of cyanate ions. Methylamine, CH3NH2. Methyl, telling me I have a CH3 group. Amine, meaning it's nitrogen. CH3 tells me C combined with 3 hydrogens. N, H2, and a lone pair on that nitrogen. Everything here has formal charge of 0. Okay, 21. This is one of the challenge problems out of the back of my general chemistry textbook. Phosphorus acid, H3PO3, has the structure HO2PHO, in which one hydrogen atom is bonded to the phosphorus atom and two hydrogen atoms are bonded to the oxygen atoms. For each bond to a hydrogen atom, decide whether it is polar or nonpolar. Assume that only polar bonded hydrogen atoms are acidic. Write the balanced equation for this complete neutralization of phosphorus acid with sodium hydroxide. A 20 ml sample of phosphorus acid required 22.5 ml of 0.1250 molar sodium hydroxide for complete neutralization. What is the molarity of H3PO4 or H3PO3 solution? Okay, let's dissect this. So, phosphorus acid H3PO3 has the structure HO2PHO, in which one hydrogen atom is bonded to the phosphorus atom. Two hydrogen atoms are bonded to oxygen atoms. For each bond to a hydrogen atom, decide whether it is polar or nonpolar. Assume that only polar bonded hydrogen atoms are acidic. So let's do that first. I've got your phosphorus, and it says my phosphorus has one hydrogen bonded to it, and two hydrogen atoms are bonded to the oxygens. I've used up my H3, my P, two of my O's. I'm going to put my last oxygen here. Why double bonded? Because add up your valence electrons and add up your formal charge. And you'll see that it needs to be double bonded there. Everything has a formal charge of 0 now. And it says, for each bond to a hydrogen atom, decide whether it is polar or nonpolar. Assume that only polar bonded hydrogen atoms are acidic. This is nonpolar. This is polar. This is polar. You can go back and check your electronegativity if you're unsure or don't believe me, but otherwise you can just trust me and move forward for now. This means, though, that I need two equivalents of NaOH to pull off two protons, because every sodium hydroxide will pull off one proton. So I need 2 moles of NaOH for every 1 mole of phosphorus acid. This will give me Na2HPO3 plus 2 moles of H2O. Then it says a 200 ml sample of H3PO3 requires 22.50 mils of 0.125 molar NaOH for complete neutralization. What is the molarity of the H3OP solution? So I want number of moles H3PO3 per liter of solution. I know that I have a 0.1250 molar solution of sodium hydroxide. By the way, up here, if you're unsure why, this is like you're writing 2H plus OH minus, giving you 2H2O. It's your net ionic equation. Those two protons require 2 moles of hydroxide. Back to the problem at hand. So 0.1250 moles of NaOH per 1 liter of solution, and it required 22.50 milliliters, which is 0.02250 liters of NaOH solution. I see I have 1 mole of H3PO3 for every 2 moles of NaOH. And it was a 200 ml sample of H3PO3. So 0.2000 liters of H3PO3. Let's see. This cancels my moles of hydroxide, liters of hydroxide. I now have moles of H3PO3 to liters of H3PO3, and I get 0.00703 molar H3PO3. I expected the number to be pretty small, to be honest with you, just because it had so much H3PO3, 200 mils, with so little hydroxide. An ionic compound is the following composition by mass: magnesium 10.9%, chloride 31.8%, oxygen 57.3%. What is the formula name of this compound? Write the Lewis structures of the ions in this compound. So this is doing empirical formula and then figuring out the Lewis structure. Remember, for empirical formula, first thing you need to do is find the moles. So number of moles of magnesium. We have percent, so we can assume we have 100 grams. 10.9 grams of magnesium converted to moles of magnesium. 24.31 grams of magnesium. 0.448 moles of magnesium. Number of moles Cl, 31.8 grams of Cl. 1 mole of Cl, 35.45 grams of Cl is 0.897 moles of Cl. And number of moles of oxygen, 57.3 grams of oxygen. 1 mole of O to 16 grams of O. People mess up this a lot. You only use 32 if you're dealing with the diatomic. When you're talking about just oxygen, it is 16. 3.58 moles of oxygen. Divide all by the smallest number, which is 0.448 moles. I get 1 magnesium to 2 chlorine to 8 oxygen. So MgCl2O8. Now this may be hard to see, but this gives me MgClO4 2, which is magnesium perchlorate. Mg2 plus and 2 moles of ClO4 minus. So let's show out the Lewis structure of ClO4 minus. The Mg2 plus is just going to look like this. There's Lewis structure, it's a Lewis dot structure, it doesn't have any electrons. But the perchlorate, ClO4 minus. So I've got, let's see, 1 chlorine, 7 valence electrons, 4 oxygen, 4 times 6 valence electrons. So what, 24 plus 7. I cannot do math that fast in my head. 31 plus a negative 1 charge, 32 valence electrons. Connect all your oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Check your form. Everything has its octet. Check your formal charge though. Each of your carbon, or each of your oxygen is -1 right now. Your chlorine, 7 valence electrons, no lone pairs, 4 bonds. Has a +3 charge. It wants you to minimize that. How can you minimize that? Multiple bonds. How about we donate a pair of electrons from each of these oxygens? Now, this oxygen still has a -1 charge, but everything else has been minimized. Compound of tin and chlorine is a colorless liquid at room temperature. The vapor has a density of 7.49 grams per liter at 150 degrees C and 1 atmosphere pressure. What is the molecular weight of this compound? Is the compound ionic or molecular? And draw the Lewis structure of the molecular ions. So now we're pulling in the ideal gas law, or a version of the ideal gas law. We know we've got tin and chlorine. So SN and Cl, some combination. The vapor has a density of 7.49 grams per liter, 150 degrees C and 1 atmosphere. I want to know molecular weight. Remember the equation for this? Density is equal to molecular weight times pressure over RT. I can rearrange this. Molecular weight is equal to density times pressure, times R, your gas constant, times temperature divided by pressure. So let's go ahead and solve that first. Solve for your molecular weight. The density is 7.49 grams per liter. R, your gas constant, 0.08206 liter atmosphere per mole K. Temperature is 151 degrees C, but we need this in Kelvin so we can cancel out Kelvin. So plus 273 K divided by our pressure, which is 1 atmosphere. We find our molar mass here to be 261 grams per mole. Remember, everything's canceling out here. So this gives me Kelvin, which cancels here. Atmospheres cancel here. Liters cancel here. And I'm given grams per mole, which is my units for molar mass, 261 grams per mole. I know I have some kind of formula of SNXCLY. Well, tin is equal to 118 grams per mole. And chlorine is equal to 35.45 grams per mole. If I had 2 chlorines, or 2 tin, I wouldn't have any time for, if I took the mass of 2 tin, that would be 118 times 2, let's say 120 times 2 for simplicity, that'd be 240. There wouldn't be any mass left to add the chlorines in there. So obviously that means I only have 1 tin. So 261 minus 118 gives me the difference. It tells me how many chlorides I have. I find my formula to be SnCl4, or what we can call tin 4 chloride. And draw the Lewis structure. Now, most people look at this and say, but it's a metal and non-metal. It's an ionic compound. Not if you look at the electronegativity difference. If you look at the electronegativity difference, it is actually covalent. We'll have our tin in our center. And our 4 outer chlorine atoms. And this is your Lewis structure of tin 4 chloride. The 2 carbon-oxygen bonds in acetic acid, CH3COOH, have different bond lengths. When an acetic acid molecule loses the hydrogen from the OH group forming the acetate ion, the 2 carbon-oxygen ions become equal in length. Explain. So I've got carbon bonded to 3 hydrogens, bonded to a carbon. That carbon has 2 oxygens. One is an OH, one is a double bond O. This is acetic acid. It's talking about the bond here and the bond here. Right now, these bonds are different lengths. This is a double bond, so this is shorter. This is a single bond, so it is longer. But when I lose this hydrogen, that's why it's an acid, it loses that hydrogen to an OH group, it forms a compound where those bond lengths are equal. What's happening? If I react this with hydroxide, what I form is either this or this. Hopefully you recognize these are resonance structures. Which means that neither one is actually true. They both just help to best represent the actual molecule. The actual molecule is a hybrid of the two. So the best I can draw the actual molecule is where it's a partial double bond between these two oxygens. They are now equivalent. They now have the same length. And use resonance to describe the electron structure of nitromethane CH3NO2. So that is also drawn out the way it's connected. CH3 NO2. The nitrogen is bonded to two different oxygens. This is one possible structure. I could write it as this as well. And if we really wanted to be specific, we could say it could also exist with just single bonds to those oxygens. But let's look at formal charge here. If I look at formal charge, each of these hydrogens are 0. This carbon is 0, and that's valid for all of the structures. Hydrogen with 1 bond, carbon with 3 bonds, always 0. This oxygen is 0. Oxygen with 2 bonds and 2 lone pairs will be 0. This oxygen is 0. Now, the nitrogen, if I would look at nitrogen, 5 valence electrons, 2 lone pairs, and 4 bonds. This is not valid. This would not have a lone pair right here. I drew those by accident. I wasn't thinking about it. That cannot do it. This would only have 4 bonds. It can't have any lone pairs there because it can't put that many electrons in. So minus 4 bonds gives me an overall +1 charge. +1 charge here as well. I'll deal with the last one in a sec. Oxygen here, 6 valence electrons, 6 lone pair electrons and 1 bond. Overall, -1 charge. -1 charge here as well. Now this last one, these oxygens would have a -1 charge. This nitrogen is a problem though. This nitrogen does not have an octet. It wants an octet. So this is not a valid Lewis structure. Because we haven't given nitrogen its octet. I see students write stuff like this a lot, which is why I'm putting it in the video to show you guys, like, it's easy to think about it, oh, well, this is right. But if I have all my electrons here, I don't have any to give to that nitrogen. This cannot exist. So this one, completely invalid. It's not going to be one of your possible structures. It will be one of these two structures, which are equivalent. These structures are chemically equivalent. Or you can say they contribute equally to the resonance hybrid. They both have overall nitrogen with a +1 charge, one oxygen with a -1. The oxygens are equivalent. These both contribute equally to the overall structure.